everyone. Welcome to the second lecture. The second lecture of the undergraduate seminar series for 2024. The first one for the second semester. Our first speaker is Lourie Bosman. He's a third-year physics student, and today he will be talking about an interesting problem involving hats. And with that problem, he'll introduce something essential to mainstream mathematics, known as the Axiom of Choice.
Thank you all for coming. I did not expect this many people, so I appreciate it. Yeah, today's focus will be on a really interesting property of math, the axiom of choice. Now, for those of you who are a bit unfamiliar, an axiom is essentially just a rule or a property in math that we will into existence. We say this is true because it is true, that's that, and all other math comes from that property. For instance, one that you may be familiar with is something like additive commutativity. In the reals, which just says that if you have two numbers in the reals, it doesn't matter which way you add them together. This fact cannot be proven from other statements. We assume this to be true and go from there, basically. Axioms tend to be a bit boring, usually, because, for instance, with this commutativity, of course two numbers add together in the same direction. Why wouldn't they? It doesn't result in anything strange later down the line. Typically, it's only when you ignore these axioms, when you ignore commutativity, when the interesting mathematics starts to happen. The axiom of choice is an axiom in set theory, but unlike most other axioms, it creates some pretty strange results down the line. And it's quite an innocuous statement if you just read it on its own. For any possibly infinite collection of non-empty sets, you can get this new set that contains one element from each of those sets. That's where the word choice comes from. You choose these elements from each set. But despite it being innocuous, it can lead to some completely, almost paradoxical results. The most famous of which, I think, is the Banach-Tarski paradox. Banach-Tarski paradox, which illustrates a way in which you can take a sphere in 3D space, an infinite collection of points, and then by separating those points into finitely many boxes or sets of their own, and then translating around and moving around and rotating, you're able to create two new spheres that are identical to the one you started with, literally creating something out of nothing. And that paradox only happens when you assume the axiom of choice to be true. If you want to read up on this paradox, it's super interesting. There's a pretty famous Vsauce video on the topic. We will not be discussing this today. Instead, I'm going to be describing the weirdness of the axiom of choice using hats. More specifically, a problem concerning hats, and it goes like this. A tyrant, evil tyrant, has captured a number of mathematicians, and for now we're just going to say 10 mathematicians. He's captured them and put them in prison, but he's a bit of a sucker for math problems, so he decides, okay, I'll have some mercy on you, and say, tomorrow I'm going to put you all into a room, and everyone is going to be put into single file, facing the same direction. Each mathematician will be given a hat, red or blue, and the goal is to guess your own hat color. So the mathematicians can see in front of them, so number one, the back of the row, can see all the other mathematicians, number two can see all but the first one, etc., etc. And when they're in the room, they cannot communicate. The only communication that's allowed to happen is beforehand, when they strategize together, and when they're in the room, they guess their hat color out loud, and the rest of the mathematicians can hear what they guess. So, my question to you is, how many of these people can we save? To solve this problem in the most efficient way possible, let's start with the worst solution, which is just everyone guesses, right? Everyone has a 50-50 chance of guessing correctly, so you'd save statistically about 50% of the mathematicians. Not very good. However, you can obviously improve this. For instance, the first mathematician, the back of the line, in his guess, he has zero information going in. He just receives a hat and he has to guess a color. So we can use that guess to convey information to, say, the second mathematician by simplest way possible, just guessing the hat color in front of the first mathematician. Then the second person will hear that guess and immediately know what hat they're wearing. One guaranteed save. And I should mention, for this problem, it's useful to talk about how many mathematicians you're guaranteed to save instead of like working with probabilities. It just makes it a bit easier. So let's go through the process of that strategy. So I'm going to make a little line here of mathematicians. 10. And then we're going to give each mathematician some hat. Let's say red, red, blue, red, blue, blue, red, blue, red, red. Now the first one can see everyone in that direction. So the first person to guess can also see this hat color. So they might as well guess red. But now this mathematician knows what their hat is. So they would guess red, and this is a guaranteed save. But now the third mathematician, once again, zero information, might as well use that guess for the benefit of the rest. So they guess red, and see here they're guessing correctly, so this is about 50-50. But now the fourth mathematician knows what their hat is, so they guess red. And you go down the line, and in the end you're guaranteed to save 50% of the mathematicians. But surely we can do better. Because this very first guess, is woefully inefficient. This first mathematician can see everyone down the line, not just the second person. So if there's some way for us to encode all that information into this first guess, we can convey information to all the other mathematicians, right? And here's where I'm just gonna sort of give you the solution, because one way to think about it, one way to come to the solution on your own is we have a sequence of hats, and we want to convey some information about that sequence in a binary fashion. So either red or blue. And the best way to do that is to work with parity, even or odd. Any natural number can be either even or odd. It's a binary function. So what we can do, erase this, is we can take our mathematicians, give them their hats, and then the first mathematician can look at all the people in front of him and see, well, there are 4 red hats. 4 is an even number. So what if we convey that evenness into this guess, say by guessing blue? So now we're going to decree and strategize beforehand to say that red will imply odd and blue will imply even. And we're counting the number of red hats. So this is just part of the strategy beforehand. So now the first mathematician guesses blue because there's an even number of red hats. But now the second person also counts an even number of red hats, which means that they can't be wearing a red hat, because otherwise this remaining one would be here. So the second mathematician knows they're wearing a blue hat, and thus gets blue, and this is guaranteed to be correct. And now the third mathematician also sees an even number, which means combined with the information of the second person guessing correctly, guessing blue, the third mathematician also knows they have to be wearing a blue hat. The fourth mathematician now sees only these three red hats, but the person before them guessed blue, an even number. Since these things do not agree, they have to be wearing the remaining red hat. Also a guaranteed save. And it goes down the line, and eventually you reach the end where the last person or the last two people guess correctly, and the last mathematician, combining all the information that they are there, for instance, let's say from this point onwards, I guess, right? This is this implies that this person is seeing an odd number of red hats in front of them, and then this person guessing blue implies that they're seeing also an odd number. They agree with this guess, and so does the ninth person. So the last mathematician will know that they have to be wearing the very last red hat, and so you're able to save everyone. Save the first mathematician. Right, so this is the finite case. Very cool. And there are a lot of variations to the problem. Some of them are quite fun. You could, for instance, try more hat colors, or you could have mathematicians face in different directions. You know, go try this on your own if you're curious. Today we're going to change the number of mathematicians, but we're going to have to get a little bit more creative, because clearly this solution works for any finite number of mathematicians. It could be 2, it could be 10, it could be 1 million. You will always be able to save everyone save the first one. So let's try infinitely many mathematicians. So once again, we create a setup where we have mathematicians standing in a line and they can see in front of them. But now it just extends to infinity. Each one is given a number, and for the purposes of this problem, the mathematicians also know their place in the line. So the first one knows their position at 1, second one knows their position at 2, etc. And now, how will you even start? Right? Because now this parity trick will not work at all. Okay, well, let's go one step back and try something. In one of our previous solutions, we tried the solution where the first mathematician guesses the color in front of them, and then this person knows what hat they're wearing, etc., etc. And so you'd be able to save half of the mathematicians. But this solution is actually quite terrible, because a countably infinite number is still not saved, right? The number of mathematicians getting saved and not saved is equally infinite. So this is not a very good solution. Is there a way for us to reduce this number to some finite amount? Alright, well, this is where our favorite axiom of choice comes in. We are going to employ a number of kind of sort of high-level mathematics, so please stop me if you're not following. Okay, yeah. I'm going to start this problem by just changing up our notation a little bit. I'm going to denote our numbers, our hat colors, with numbers. Specifically, I'm going to call red hats 1, and I'm going to call blue hats 0. Surely this won't help us down the line, right? No, this will become very useful later on, but for now it's just going to be a shorthand. You don't have to worry too much about that. Now, our strategy, once again, let's think about how we solve the finite case. The first mathematician was able to condense information about the entire set into that one guess, into a binary 1 or 0, essentially. So we need to be able to condense information about the entire set, or we need to be able to group information about the entire infinite set. Or in other words, you need to create a sort of partition. In math, whenever you hear the word partition, your mind should immediately jump to equivalence relation. What is an equivalence relation? It's a really simple thing. It's a binary operation x between two numbers or two objects, say x and y, and you say that an equivalence relation, or x and y, you say that x and y are equivalent, right? And an equivalence relation has to satisfy 3 properties for it to be a real equivalence relation. It has to be reflexive, every element is equivalent to itself. It has to be symmetric, so it doesn't matter in which order you do it. And also, it has to be transitive. So if one thing is equivalent to another and then to another, the endpoints are equivalent, essentially. What an equivalence relation does, and the reason it's so useful, is it takes any set that you apply on, and it partitions it perfectly. So every element in that set belongs to one and exactly one group, or equivalence class, as we call it. So our goal is going to be essentially to take every possible sequence of hats, of 1s and 0s, and find some equivalence relation to partition that set, and then go from there. Now I'm going to, once again, just kind of give you the solution. Finding this is quite tricky on your own, but you can check this for yourself. One equivalence relation that you can apply to this set is this. You can say that 2 sequences of hats, say x and y, are equivalent if they differ at finitely many places. Check that this is indeed an equivalence relation. Let's go through the process. Is x always equivalent to itself? Well, yeah, because it differs at 0 places, which is a finite number. And this statement here is symmetric in its nature, so the equivalence relation is also symmetric. And lastly, if 2 sequences, say x and y, are equivalent, and y is equivalent to some z, then, well, x and y differ at finitely many places, and y and z differ at finitely many places. Let's say d1 and d2. Then x and y have to differ at a maximum of d1 plus d2 places, which is also finite. So this is indeed an equivalence relation. One thing that's sort of subtle about this, but is ultimately going to be the solution to the problem, is that we split the entire set of sequences, we partition it, using a finite property, the amount of places where they differ. And the great thing is, any finite number has a parity. So could we potentially apply the same strategy as last time to this equivalence relation in some way? Well, yes, that's why I'm asking you. The solution is going to go like this. Mathematicians have a superpower, the axiom of choice. They're able to construct a new set that contains exactly one sequence from each equivalence class. and we are assuming that they have a perfect memory and perfect calculation power. So they've all memorized this set of representative sequences from all the equivalence classes. So then let's go through the process. Let's say these mathematicians are currently in a sequence that looks like so, like 1, 1, 0, 0, and from here on it's just zeros all the way down. And let's say, for argument's sake, that the sequence pertaining to this equivalence class that they've picked is just the sequence of zeros. Well, let's go through the process. The first mathematician sees the sequence, the entire sequence, laid out in front of them, which means they are able to identify in which equivalence class they're currently in, right? Because remember, the fact that they differ at finitely many places means that at some point, this sequence that they're currently in will be exactly the same as the representative sequence. So it identifies, oh yeah, we are in this equivalence class represented by the sequence 0, 0, 0, etc. And now what he has to do is he just counts up the number of places where this sequence they're in right now differs from the representative sequence. Of course, they can't see his own hat, but in front of him, he sees 1 red hat, and the rest is 0. So it differs at exactly 1 place. 1 is odd, and then applying the same strategy as last, he just guesses 1. But now the second mathematician sees the same sequence laid in front of him, and for the same reason can identify the relevant equivalence class. And this mathematician sees only zeros in front of him. It differs at 0 places with the representative sequence. Since that information, 0 is an even number, so that does not align with what the first mathematician guessed. So they have to be wearing a red hat. And then once again, this is guaranteed, and the same process applies down the line. You're able to save everyone except the first mathematician. That is insane, right? This should not be possible. You have infinitely many of them, and the sequence of hats can literally take any form. It could be all zeros, or it could be completely random, and yet they're able to save everyone but the first one. If that doesn't impress you enough, and if that doesn't feel strange enough, I'm gonna illustrate some more weirdness of the axiom of choice using measure theory, a little crash course in measure theory. Don't worry, we're not going to be doing honors level math today. We're just going to ultimately just discuss some properties of measure theory and work with that. And the goal is going to be to construct a set that does not have a measure. But before I get ahead of myself, what is measure theory? What is a measure? The Lebesgue measure is a generalization of the idea of size. In the way that, say, a line segment has a length and some area, some surface as an area, the Lebesgue measure is a generalization for all these notions of size. And it's actually quite intuitive. For instance, if you consider the real line, this segment that goes, say, from 0 to 2, its measure, let's call this thing L. Okay. Let's call this set L. Its measure, which I will denote with mu, is just 2, the length of the line. Or if you have some weird surface, it doesn't even have to be a square, just any surface, say, what it is, its measure is just the area of that surface. very, very intuitive. Oh, and also I should mention that a point, a single point, is 0-dimensional. Its measure is always 0. Now, the Lebesgue measure has a very rigorous and specific definition that's quite complicated, but we don't even need that definition. Because using just a couple of properties for what we want a measure to behave like, we can prove that a set does not have a measure. It can't possibly have one. And these properties that we'll be using today, I'm going to list them here. The first property that we're going to use is invariance under translation. The measure is invariant under translation, which just means that if you have some set, if you have some random set that's get created here, call this thing S. If you construct a new set by just moving the set around, call it say S prime, these two sets will have the same measure. Of course, this works in any dimension. It doesn't have to be just on the real line, but for our purposes today, the real line is sufficient. Property number 2 is additivity. Which also very intuitively says that if you have two sets and they are disjoint, so they do not intersect at all, and for all these we're assuming that the measure is defined, but yeah, so if you have two disjoint sets, the measure of their union is just equal to the sum of their independent measures. So if you have two, say, two surfaces over here, each with their own measure, as long as they don't intersect, you can just add up the measures to get the measure of the total shape. Again, very intuitive. We will be generalizing this notion to sigma additivity, which just generalizes this to countably infinitely many sets. So if you have a countable collection, let's call them AI, where it's just a natural number, then the same trick applies, as long as, oh sorry, they're disjoint. These sets are just disjoint. So the same trick applies here. The measure of the union of all of these sets is just equal to the sum of their independent measures. And then the final property that we'll be using, final property here, is just that the measure of a line segment is just its length. And this works for closed and open intervals. This works for closed and open intervals because of additivity and the fact that single points have a measure of 0. A final property that we will sort of be using, well, that we will also be using, but it's not like fundamental, it comes from these properties, is that if a set contains another set, then the contained set's measure will be less than or equal to the bigger set's measure. which, yeah. Alright, with these properties, we can start. And the way that we're going to construct this set, well, honestly, we've already constructed it. We're just going to represent it in a different way. We're going to take our set of representative sequences. You know, the equivalence classes each have some sequence that's represented by. But now, instead of working with sequences of red or blue hats, zeros and ones, we're going to convert a sequence, like so, into a number by simply putting a 0 point in front of that. Because now this number, or this sequence, becomes a real number. And in particular, in binary, if you make all these numbers to be binary representations, then every possible sequence that you can construct of red and blue hats is just every real number between 0 and 1. If you're not familiar with binary, by the way this works is the same as a decimal. It's just you take the number there and you say 0 times of, and you take that number there, and it becomes 1 times a quarter, etc. Right? Yeah, so now our possible sequences of red and blue hats are real numbers between 0 and 1. And we're going to specifically consider the set of representative sequences. Call it S. So S is just going to be the set of all numbers x, such that x represents its respective equivalence class. Let's call it A or AK. So we just take this set, which once again we could only find this set using the axiom of choice. What I'm going to be proving today, or right now, is that this set cannot have a measure. No matter how you define your measure, as long as it satisfies those couple of basic properties, the two things don't mesh. Alright. So one important thing to note about this set is for any x and y in S, these two numbers cannot be equivalent. I don't know if that's simple for non-equivalent, but it's just okay. Because if they were, then you would have two numbers from the same equivalence class, and hence a contradiction. We only want exactly one element from each equivalence class. So that's one property that we'll be making use of. And now we're going to apply a little trick to this set. Consider all the rational numbers between -1 and 1. As you hopefully know, the rationals are countable, which means that we can take all those rationals and put them into a sequence. These are all the rational numbers. But we're going to place a further constraint on this sequence, and we're only going to consider the rational numbers that terminate in binary. The reason we're doing this is this equivalence relation that we defined based our equivalence classes on, in this new world of binary numbers, binary real numbers, that equivalence relation is the same as just saying two numbers differ by a number that terminates in binary. So we're going to specifically consider every possible number that terminates in binary. And we're going to take them between -1 and 1. So we will construct a so these numbers are indexed by I, and it's countable, so we're going to construct a new countable collection of sets using our original set, like so. Define Si as simply x plus Ri, where x is just every number in S. This is just taking our set S and moving it around by some number R. So if you have, say, 0, 1, minus 1, and this is 2, but this is technically 1, 0 in binary if you want to be pedantic about it. So for instance, say if you have your set S as a bunch of points in here, every Si will just be taking those points and moving them over by some amount Ri. And since Ri is between -1 and 1, this new collection will span from -1 to 2. So that's one thing to take note of. And now we're going to prove two really important properties of this collection of sets. Point 1. Every Si is disjoint, this collection. So, yeah, every Si is, or Si is J is disjoint if I is not equal to J. And point 2, the interval 0 to 1 is contained in the union of all of these sets. Proving this is a bit tricky, so just bear with me, this is where it gets technical. But to prove 1, we're going to do this by contradiction. Just assume that these sets are not necessarily disjoint, so there exists some Si Sj such that you have some number, call it xi in Si, and some number xj in Sj, such that xi equals xj. But then, from that, because xi is in Sj, it can be written, xi is in Si, it can be written in the form x plus Ri, where x is just some number in S, and the same holds for xj. Now, for some y in S. So from this equality, we have x plus Ri equals y plus Rj. And then just rearranging a little bit, we get that x minus y equals Rj minus Ri. But from here, since Rj and Ri are both numbers that terminate in binary, this number terminates in binary. Which then implies that x has to be equivalent to y. But as long as x and y are not equal, they cannot be equivalent. And since Rj and Ri are also not equal, x and y are not equal, and we get a contradiction. So that's the first point. We prove that the collection of sets is disjoint. And to prove the second one, you simply pick some number x the interval 0 to 1, then we know, since x is in this interval, x is equivalent to y for some y in S, which then implies that x minus y equals r, where r is some number that terminates in binary. But that sequence over there contains every number that terminates in binary between -1 and 1. And hence, hence we have that x is equal to y plus rj, where j is some index over there, and thus x has to be in the set Sj, and it's contained in the union of all SIs. Okay, so with that busy work out of the way, we can get to the finale, which is just that using those two properties and combining it with these three properties, we know, first of all, that the measure of these SIs is just equal to the measure of S, since you construct SI by translating around. But you also know that that the measure of each SI, of the union, is going to be less than or equal to 3 because it's contained in the interval -1 to 2. But it's also bigger than or equal to 1 because 0 is contained in the union, and 0 to 1 is contained in the union. This set has a measure of 1, hence this set has to have a measure bigger than or equal to 1. And then finally, using our sigma additivity, we know that the measure of the union of this union of SIs is equal to just the sum I naturals of each SI, which is then just equal to the infinite sum, measure, since these two are equal. So what we've got here is a real number that has to be added to itself infinitely many times to get a value between 1 and 3, which is impossible. And hence, this set over here cannot have a measure. And this result is only due to the axiom of choice. If you ignore this thing, if you work with this, the regular Zermelo-Fraenkel axiom that excludes the axiom of choice, the Lie measure works on any set. Every set has a measure, a well-defined measure. But it's only when you introduce this cheeky little axiom that it stops to work. So, that's about my story. Hopefully you're convinced that the axiom of choice is weird. Any questions?